Okay, let's take a swing at Chapter 9. This is going to be one of the shorter chapters here. And we've got welding, bonding, and permanent joints. One of the things I'd like to remark about this chapter, we're going to look through all of it here to some degree. So we're going to be looking through all of this, but it's not the most complete chapter. So it's a good general resource. Oops, let's get rid of that. It's a good general resource, and it's got some nice references. Um, and I've looked for a better book, but um, simply not enough time to give this the proper treatment. This part right here, this is not really, this does not provide sufficient material to fully analyze and design welds. Um, I'd use these slides as a guide for what you need to know from Chapter 9 for this course, but if you find yourself in need of checking welds, designing welds, or otherwise implementing some kind of weld or doing it yourself, you definitely want to check out some additional resources. This is just sort of topical content. Along with that topical content, uh, you might see some type of funny dimensioning symbols on a drawing. And if you see those are probably calling out welds. Now this is all pretty complicated here. They've got tails and arrows. We've got the circle here. We've got all this stuff, length, and wow, that's a lot of stuff. I'm gonna make it a little simpler for you than all this stuff. So wow, lots of stuff here. So it's actually going to be a little simpler than that for you. But before we get to that, we've got the arrow side. That's where the joint line side or area to which the or near the member to which the arrow points. Then the side opposite the arrow side is the other side, and then we can also have the shape of the weld shown in the on the weld symbol, which some examples are shown below in this table here. For instance, in a bead weld, you would have a couple of plates joined together like this. Fillet weld. So let me draw these over here. You know, a bead weld would look something like that. A fillet weld would look something like that. So once you realize that, the plug or slot weld means that the two pieces are some distance apart. So you've got a couple of parts like this, and then the weld goes in between them. Fill that in. So that's the first three. You know, if this is 1, 2, and 3, that's 1, 2, and 3. Square weld is actually something like that, where you're squaring up two pieces. So now the V, bevel, and U should make a little bit more sense. So as example 4, let's skip to example 7. You'd have two pieces that look like this, and then you'd fill this space with a weld. That's a U weld. That's not a my weld, that's a U weld. All right, so that's kind of, so the weld symbols themselves are fairly pictorial in nature. Let's look at some welding symbol examples. And here's how I said I'm going to make it a little simpler for you. So concentrate on these simpler welding callouts or symbols. So let's go back up to page 3. So I'm never going to give you something as complicated as this. It's going to look like more like this. So if I you should be able to find in the book, in an open book. So you should be able to find these in an open book exam. To find and identify. Whoops, I guess that went off the page here. So you should be able to find and identify these simple welds in the book. For the final exam. And I'm not going to stray too far from what's just directly in the book on these simpler examples. Same thing here. These simpler welds potentially on the final. And if it's not in page 7, yeah, there it is. Okay, so we have the J weld, U weld, and let's go back through all these simpler welds. So in the first page of welding simple examples, we have this here, which is the size. So this is the weld size. It's a fillet weld. As you can, this means it's a fillet weld. And then this means that it's both sides, right? What's interesting about this next one is it's on both sides, but when you see it like this, it means that it's staggered. Whoops. So it alternates side, so you can't see that from this view, but this is on one side, this is on the other side, and this 60-20 over here is the width and length in between. So this is the width of the weld and the length in between. And then here we see this circle here. This circle indicates that it's all the way around. So when you see it from the front, it's all the way around. It's on one side only. So it could have been on the inside, could have been called out both sides, in which case you'd have a weld on the inside as well. So this means one side, and with the V, it's a fillet weld, and it's got a size of 5 millimeters. All that in that view, in that welding symbol. And similarly here we have different types of V welds. 45 and 60 here. 45 and 60 are the default for the V welds and or the X welds and V welds, bevel welds. Here we see the different implementation of, if there is none, this implies, whoops, getting a little too happy with the Surface Pen here. This implies 60 degrees. This implies 45 degrees. So if there is no angle call out, you go to the defaults for the double V or the single V, whatever you want to call it, of 60 and 45. This is loosely speaking what the welds will end up looking like, the little blobs before you grind it off. And then here we have additional symbols, a different type of fillet weld here where you have a beveled surface. That's probably about as complicated as it gets. So this is complicated as it gets in this course. This one here isn't very intuitive, but just by itself. But when you couple it to the actual drawing, it becomes pretty clear that you just want to fill in, a fillet weld there at that location. I would have moved this whole symbol up over here to be like this. That way it's pointing to where you're actually welding. It doesn't tell you a size, so there's no size, so just fill it. So there's no size given. Just fill it, not fill it, fill it. Same thing with all these, there's no size given. So you just have to cover the surface, fill the volume. So in all these, no size. So cover the surface, or fill the volume. Whoops. And now you see, details of all these, the U-weld, J-weld, and square weld. So this is the U-weld, J-weld, square weld. And here's so these last 3 pages. Let me scroll back a little bit. So starting at page 5, these are some simple weld symbols you're responsible for. Same thing on page 6 and page 7. You should be able to mix and match or identify these like in a multiple choice or multiple answer type of question. Match the weld symbol with the or weld description with the picture, or any permutation of that weld symbol. Basically identifying a weld symbol. Tensile stress, we're going to, they get a little bit complicated later on stresses. We're going to keep it fairly simple to tensile and shear stress in a butt joint. This is pretty straightforward. We're going to try to identify the stresses in a butt joint here. And in this case, stress is force over area, and the area we're considering is essentially the length of the weld divided by, or times the throat height. So the throat height here does not include the extra reinforcement material, the little bubble on the top and the bottom. So that's the extra reinforcement material is the bubble on the top, and bottom doesn't count. So the reinforcement, that reinforcement bubble may add some static strength, but it's actually bad for fatigue. You get a stress concentration here for fatigue. So generally those are those little extra bubbles are ground off, polished up a bit, get it looking like a nice flat smooth surface without any corners or scratches. But anyhow, here's the meat of it. This is a tension loaded butt joint, and the tensile stress, the normal tensile stress, is just the separating force divided by the throat height and the length of the weld. Pretty simple and straightforward. Same thing with shear. In this case, notice that the equation looks the same. So this looks the same. Whoops. This looks like the same formula as 9.1, but it isn't because the forces are in a different direction. So in this case, we have shearing forces, but they kept the magnitude as F, which is a little confusing, but bear with it. And we're still using the throat height without the reinforcement bubbles, and the length of the weld as the area that we're considering. This one's a little bit more complicated, stress and transverse and parallel fillet welds. So these are two different welds here. So we've got the transverse and the parallel. So, but in either case, they're looking at the throat length um, as H as the that width right here. They're considering that to be the throat width. And if you have separating forces in this case, we're looking at shear stresses in this case, not tensile stresses. And you would use this formula for these two welds to determine the shear stresses that are acting on these transverse or parallel fillet weld. And that's pretty much it for the stresses. We're going to skip sections 9.3 and 9.4. And that's stresses in welds due to torsion and bending, so torsion and bending. And those type of loadings certainly happen to welded joints. Unfortunately, the main reason I'm excluding this, I would love to include it, but the sections are not very clear and they're overly complicated. They appears to have several errors and inconsistencies. I've worked through the examples myself, and the material is limited in value to this preliminary design analysis anyhow. And in practice, you'd use finite element software for a preliminary design anyhow. And most importantly, usually you're applying welding codes for the final weld specifications. You might double check the stresses. So you might, let's see here, double check the stresses. And you can do that with FEA. You don't need any formulas. I strongly suggest using FEA, particularly SolidWorks. You can put in the material properties, and but primarily apply the appropriate welding code. And that's really, the book doesn't include those. Those are really up to you to find for your application. Library is a good source, right? Or American Welding Society. So I would say look at library or American Welding Society. Those are the two main sources for welding codes. Strength of the welded joints. Here's some things to keep in mind, that you have to check for failure in the parent material and in the weld. And often the welded material is stronger than the parent material. And furthermore, the parent material could experience heat treatment near the weld. Actually, it will. There's a lot of burning going on, high heat. So if you start with a cold drawn parent material in the vicinity of the weld, it may become more like hot rolled in the vicinity of the weld here. Okay. And as I mentioned in the previous slide, more often than not, you're usually designing welded joints by following codes rather than the conventional factor of safety method. And as a result, they have some tables here, but this is tables 9.3 and 9.6 are useful, but it's really, I mean, it's really limited. This is really limited. Like I said, there's a whole society set up around this, and there's enough books to fill a small building on welding codes. So there's really not much that a chapter like you can put into a chapter like this. So again, check check the library or the American Welding Society. I've seen these people at conferences. They definitely exist. They're populated. They're active. They send people to conferences, and they usually have a table set up at mechanical engineering oriented or engineering education oriented um, conferences. Make a contact there. It couldn't hurt you. They also have training. So AWS has training. I know because I talked to the folks at that table because as soon as I saw them at their table, I thought, hey, this is perfect for my machine design class. I'm going to let them know about this. So here's tables 9.3 through 9.6. This is these are the American Welding Society electrode number, and then your weld strength is your tensile and yield strength are going to be, so this based on what electrode you used. Certain electrodes work better with certain materials, so you might not have that much of a choice. But this is definitely useful to know. Particularly if you're trying to back out why a weld failed, and if it failed at or near the weld, or particularly at the weld, if a weld ripped apart, you can look at what you can find out what electrode was used. Then you know the tensile and yield strength, um, and you can approximate your loads and figure out if it was a static failure or a fatigue failure. That'd be one way you could use this kind of information to dissect the failure, or you can use this for basic preliminary design. They have some permissible stresses. This is right here. This is instead of a factor of safety. So this is the equivalent factor of safety, but they're not using. They're using a code. Whoops. So they're using a code instead of a factor of safety, but they included the equivalent factor of safety here anyhow. Not that it's doing you any good, but I mean this is typically what codes are based on like that. This is also pretty useful. Allowable loads, and this is in so it'll give you the strength. So we have the strength level. Then we have the allowable shear stress. And the neat part is, this is just your, you can use this shear stress is from that formula. I think it was formula 9.2. So if you have your shearing forces, your throat height, and your weld length, this will give you your allowable shear stress. Now the allowable unit force is given in kilo-inch pounds per linear inch. So this is, or I'm sorry, kilopounds per linear inch. So this is allowable separating force. And it's given in kip per linear inch. And a kip, for those of you not in the know, is a kilopound, or 1,000 pounds. So this is per inch of weld. This is per inch, linear inch of weld. Really, all you need to know is in this line of the table right here for the allowable separating force for a fillet weld. Uh, these these are just calculated. These are just calculated from this formula. That's it. So it's um, not quite sure. I guess they just needed to fill some space with the table. This is the this is also useful if you're looking if you're doing a preliminary design. So in summary, before I get to this table, tables 9.3 to 9.6, they do provide some useful information for preliminary design purposes. So if you're putting together a drawing of a part that you're designing or an assembly that you're designing rather, and something needs to be welded, if it's a simple enough weld, you can use the book to assign a basic fillet or J or U type weld symbol and size, and then you can use tables 9.3 through 9.6 to determine if it's big enough to take the stress, or which size the fillet weld should be, like here in table 9.6. They've got a couple notes here. You can read why there's a squiggly line here, but just go off the table straight across. The dotted line has corresponds to this note here. It's just a comment on sizing, but the table still reads left to right in a line. So the dotted line is there for reference only for that last note. Everything's still supposed to be in a line here. These are the sizes, like that. The sizes don't take a sudden jump up along the dotted line, just to point that out. I'm not going to take a whole lot of time through the examples, but here they've got an example where they give you the electrode, use the Welding Code method. So they want you to use the Welding Code method, and they want to know, is the weld metal strength satisfactory, and is the attachment strength satisfactory. They give you the size of the joint and everything like that, with a 3/8 inch weld, 2 inches long. So they're giving, you can get, it's a fillet weld, so you should be able to get the throat length and everything else. There's an error according to their formula and their table, just to keep in mind. Well, first of all, let's part A. From table 9.6, there's an allowable force per unit length for a 3/8 inch E20 or E70 electrode metal, and so you can calculate the allowable force per unit length, and so that's the allowable force, and the actual force is 16.5, so we're within the range. The next part B has an error in it, as far as I can tell. That this one right here from table A20, I'm sorry, table 9.4, the allowable attachment shear stress should be 0.3 S sub Y. So they get the wrong answer there, but so this is wrong too. And then you can calculate the shear stress. Why is there a 2 here? That's not in the previous formula. Well, if you go back up to the configuration, there's 2 of them. So this is times 2. You're sharing the load, and that's why there's 2. There's 2 fillet welds. Sharing the load. So that's where that 2 mysteriously comes up. Now, if you correct it now, this is not satisfactory. So you might want to go back through and look at the very table that they have. Where was it? Yeah, right here. Shear, butt, or fillet this is the one that's incorrect. So this is incorrect in example, what was that, 9.2? Yeah, example 9.2. That goes back up to, where was that? Nope, next one down. So this one right here, they're improperly using this formula. Down here in the example problem, that's where the error is from table 9.4. If you do that, then all the answers change, and it's no longer 11 equals 11 kind of stuff. So it's not a satisfactory attachment. And we can also calculate the tensile strength or tensile stress and the allowable from 9.4. Let's just double check them, make sure that they at least got this one correct. 9.4, let's see here, butt fillet. Yep, 0.6, so this is correct. That's good. And so it was okay in tension. So the result is okay in tension, but it fails in shear. So no good. Here's some other better resources for weld design. On the internet, there's a couple of useful tables. So useful tables for weld strength. This is a good one right here. List of welding codes. Like I mentioned before, the technical and engineering section of the library, and especially the AWS website right here. AWS, that's a biggie. So, without resorting to anything on the computer beyond the internet, you actually have a lot of rich resources available, and particularly the AWS publications will get you a long way. Other things like boiler codes and all that sort of stuff, ASME and all sorts of other organizations are in charge of that. So, there's also boiler, I'd add here, boiler codes, boiler and pressure vessel codes. Those will be cross-referenced to a lot of welding codes because boilers and pressure vessels in general are generally welded up. So the boiler and pressure vessel codes, those are extensive. Those are also, you add all those up and you've got a large building full of paper. So the task here is to find the one that actually applies to the system or components that you're working with. I would strongly suggest in preliminary design, just use FEA software. And however, you're going to probably have to fudge the, not fudge, but you're going to have to, ink in your own material properties. You can use a factor safety method, and calculate the allowable stresses and all that sort of stuff. But really, the mystery here is strengths. So particularly, what's the weld material strength, and what's the component material, because it may have changed. This in the vicinity of the weld, this may have, I went off the, let me redo this because I went off the edge of the screen here. So the strengths are sometimes difficult to nail down, particularly if you don't know what electrode you're using, what will be the weld material strength, right? And the component, in other words, the thing you're welding, material was heat treated, So what's its new strength? Probably don't know for sure. You don't know how hard it was heat treated. So you might have to use an equivalent hot rolled instead of cold drawn type of material. But what if it was already hot rolled? They don't really have hotter rolled in the materials section. So your actual material um, of your the things that you're welding, the actual strength in the vicinity of the weld could be unknown. And that's why, in general, when you get down to the final weld, there's so many variables. I'm going to delete that line. This is important here. There's so many variables and unknowns, and that's really why they've developed codes. And the codes are basically developed from actually welding a bunch of stuff and ripping it apart. So and then repeating the process, getting a statistical set of data, and going on like that. Other topical information. This is kind of neat. Definitely look in the book. They've got some neat pictures, I believe, in these ones. But resistance welding, this is really common. This is a really good, cheap way of slapping a couple things together. Usually it's the important thing to note is that the two failure methods here, usually either the weld shears or the material tears. And you definitely want to avoid tensile loading on these little resistance welds. So you have two thin sheets. This is usually thin sheets of metal, and you put an electrode on either side, and bzzz, it just fuses the two right there. And what you don't want to do is you don't want to pull on that. Don't pull too hard. They do not like to be pulled apart like that. You'll rip the sheet metal. There's also adhesive bonding. This gets really um, uh, complicated. Um, there's all sorts of chemicals at this point. You have, um, there's a lot of benefits. Here's some benefits: reduced weight, sealing, reduced part count. You can just buy a tub of 55 gallon of adhesive and pump it into some small part of your assembly process. Um, there's a lot of other advantages listed here, and there's a lot of different forms. So these are different classifications. And this, what do you pick? So this is really, you know, when you need to join some things together, you're coming up with a design. What the heck do you pick? Do you actually put in a heavy duty weld that a welder puts in? Do you just take a couple of electrodes and do a resistance weld? Or do you use some sort of chemical or this should be plaster, not pasture. Should be an L in there. Plaster, pellets, tape, whatever. Um, Plastics. What do you? Is it structural, non-structural? What do you pick when you're doing this? And really, a lot of this comes down to design experience, codes, and knowing your material. And also, that the materials includes not only the things you're joining, so the materials is the things that you're joining, and the part that's welding it or adhering it, the weld or adhesive, right? So those are you need to know about what you're implementing, and maybe do some basic calculation or finite element work. Um, this is really useful here. I included this. This table is neat because you're not going to really find something, uh, you know, this detailed. Particularly, I've used a lot of this cyanoacrylate. Anybody know what that is? That is super glue. Who knew that you'd be able to find the room temperature lap shear strength of that or also known as the peel strength per unit width, right? So, if you want to find out, hey, we want to fix this part in the field using super glue, well, maybe you want to check if it can actually withstand what you're trying to do right here on the table, right? And if it can't, maybe there's something else down here like uh, anaerobic acrylic. This looks, was that more heavy duty? No, where's the 1.8? Urethane. And rubber modified acrylic. Uh, maybe you need to upgrade to something like that. But this can help you if you had a glued joint and it's not working. You might want to calculate or find from a table like this or this table what's its peel strength, and if it's not sufficient, pick something a little bit more heavy duty. And that basically concludes this chapter. Let me. That was welding, bonding, permanent joints. That certainly didn't take 2 hours and 50 minutes. So this is sort of a partial course lecture, but I hope it was informative for you. And got to reattach my keyboard here to stop the recording. And we're going to move on to chapter 10 next.